Okay, so to continue talking about powers and roots, using transformations with powers and roots. So when experience or theory suggests that the relationship between two variables is described by a power model of the form y equals ax to the p, you now have two strategies for transforming the data to achieve linearity. I want to reiterate what I said in the last video, which is you're not going to be expected to know whether there is a theory or experience in these questions that's suggesting a power model, okay? It will just be told to you. Okay, so what we did in the last one, that first transformation, was to raise your values of the x variable to the power, okay? Where the second transformation was to take the cubed root in that last problem. So take the power root of the values of y and plot the points. Leave x, plot the root of y. Okay. So what if you had no idea what power to choose, which is likely to be what our situation would be. It would just be told to us, but if we may not have a good idea, okay? Because we just may not have any idea. We might have to do research on what the problem is, what a relationship may be. So you could guess and test until you find a transformation that works. Slightly time consuming. Technology would come with built-in sliders that allow you to dynamically adjust the power and watch the scatter plot change as you do. Okay. We'll also be looking at our calculator. I'm going to teach you that in class too, though. It turns out that there is much more efficient method for linearizing curved pattern in a scatter plot. So instead of transforming with powers and roots, you could use logarithms. So using a logarithm it's a more general method that works when data follows an unknown power model, which I kind of feel like you shouldn't assume that it is a power model regardless of what you think. Instead, using a logarithm would kind of help you alleviate not knowing if it's a power model or any of several other common mathematical models like an exponential model. You're not expected to know those things. Logarithms would help you out with when you don't know. Okay. So not all curved relationships are described by power models. Some relationships can be described by a logarithmic model of the form y equals a plus b log x, okay? Whoops. So just a few things. So like the health and wealth example that we began last video with, right? So it's life expectancy versus the logarithm of the income per person, and it is a base of 10, showed a linear pattern. That's how we kind of straightened out that curve that we saw. Okay, so some relationships can be described by a logarithmic model. It helps. So like that relationship that we saw there, the book gave me that the predicted life expectancy. Okay, we knew it was a log because that we saw that in the scatter plot. It was log of the income, okay, versus the life expectancy. Go back to the first video if you want. So the regression line this is still slope. Okay. This is like what your x is on your x-axis. Okay. This is still your y-intercept. So it's still fitting a plus bx form. Okay. This is still your y-hat. Okay. Still what's on the y-axis. Okay. So after you straighten it again, now you can see how well that model works, depending on how strong your R squared is. You can tell how appropriate a linear model would be with a residual plot. And you can then, depending on the results with that, you can then use to predict other values. Okay. So taking the logarithm of the income per person of values straightened out the curved pattern in the original scatter plot. The logarithm transformation can also help achieve linearity when the relationships between two variables described by a power or an exponential model, and you may not know what that power or exponential model may be. Okay, so when we apply the logarithm transformation to the response variable y in an exponential model, we produce a linear relationship. To achieve linearity from a power model, we apply the logarithm transformation to both variables. Here are the details. Okay, so a power model has the form y equals ax to the p, where a and p are both constants. We saw that in the fish problem. We're going to take the logarithm of both sides of the equation using properties of logarithms. The equation log y equals log a plus p log x shows that taking the logarithm of both variables results in a linear relationship that happens between log x and log y. If you look carefully, the power p in the power model becomes the slope of the straight line that links log y to log x. That's what I showed you before with the life expectancy regression line. Okay. If a power model describes the relationship between two variables, a scatter plot of the logarithms of both variables should produce a linear pattern. It may not, but it more than likely will. Then we can fit a least squares regression line and do what we know what we can do. Okay, so we can arrange the final equation as log y equals log a plus log bx. Notice that log a and log b are constants because a and b are constants. So the equation gives a linear model relating the explanatory variable x to the transformed variable log y. If we fit a least squares regression line, so I just want to go down to the bottom. So to obtain the corresponding prediction for the response variable y, we have to undo the logarithm transformation to return to the original units of measurement. One way of doing this is to use the definition of a logarithm as an exponent. So let's go back and take values, cubing the x values, right? And then we took the cubed root. We took the cubed root of our y values, okay? And both were successful at straightening out your data. Let's see what happens if we use logarithms, right? So we took the logarithm base 10 of the values for both variables. Some computer output from a linear regression analysis on the transformed data is shown. So they give you a residual plot, so you know a linear model is appropriate here, okay? They definitely straightened out the curved pattern that you saw in the original, okay? They took the log of the length and the log of the weight. So based on the output, explain why it would be reasonable to use a power model to describe the relationship between weight and length of ocean rockfish. So if a power model describes the relationship between two variables x and y, then a linear model should describe the relationship between log x and log y. The scatter plot of log times weight versus log times length is a linear form, and the residual plot shows a fairly random scatter of points about the residual line. So a power model seems reasonable here. Okay. So then we want to give the equation of the least squares regression line. So we're just going to follow what we did in what we had on previous slides, okay? So that's going to tell us that we're going to do predicted y, okay? And our predicted y is here. Okay, so our predicted y is not just y or y hat, it's hat log weight. Okay, here's your y-intercept. Here's your slope. Okay, and then the log of the length. Transformed x, and you transformed y using logarithms of a base 10. Okay. So now, because the residual plot showed a linear model is appropriate, your R squared value here, 99.9%, okay? You also have a very low standard deviation of your residuals, showing that this regression line is probably a pretty good fit for that linear model. So we could go ahead and use it in order to make a prediction. You don't have to put weight and length. You could put x and y, okay? So I'm looking to make a prediction on 30, how much 36 centimeter rockfish would weigh. Okay, so here's my model. Okay, and I'm just going to simply substitute in. Oops. A log of 36. Okay, straight calculator straight calculator work here. Okay, so once you so once you get to this part, now you can take the log of base 10 of your 2.84. Okay, so in other words, I'm going to squeeze it in here. So in other words, you're taking log of base 10. I'm just going to put y for space reasons, okay? So log of a base 10 would be 10 to the power of 2.8464, which is going to give you about 702.1, and this was in terms of grams. Okay, I'm going to call that it on the transformations of logarithms video. Almost done with this chapter.